The next couple of lectures are dedicated to the theory of martingales, which are in a way the replacement of what we understand as a constant function in probability theory. This sounds boring because constant functions are not so interesting, but in probability theory it just should mean that their expectation is constant, that there's still a lot of things that can go on even if expectation remains constant over time. And whenever this is the case, we talk of a martingale, and we will see that it has numerous implications, and we will discuss and present the theory of martingales not in a very exhaustive or extensive fashion, because we will use martingale arguments and martingale concepts many times in the future. So therefore I'll try to present the whole theory really as efficiently as possible, but nevertheless I shall interject here and there first application, such that you do not get bored too quickly by what I shall present. So today we'll introduce this class of stochastic processes, the class of martingales, and we will finish with what is called the optional stopping theorem, which is already quite a little surprising in a way, and we will apply this as an extra bonus, if you like, feature of today's lecture to, again, Markov chains, and see how we can solve the Dirichlet problem for the harmonic function using martingales, or we just give another proof of the fact that the Dirichlet problem can be solved, but this time using martingale arguments, so that you can see you can argue efficiently once you have the concept at your disposal. Okay, we start lecture 9 with the definition of martingales, as I just said in the introduction. First, we recall, or we introduce the concept of a filtered probability space. We have seen already in the past that when we have a probability space, there is not only that one sigma algebra that we can use. For instance, when we were dealing with the conditional expectation, we were dealing with an alternative sigma field, which is a subfield of the given field F, to which we project. And now we want to deal with a whole range of such sigma algebras, which parameterize our increasing amount of information that we might have as time evolves. Okay, that will be the contents of the definition of a filtered probability space. And it goes as follows. If you have a probability space, omega fp, and you have a certain index set, which is in most of the cases, in our case here at least, a subset of the integers, or later in the lectures, a subset of the non-negative real line. And if we are given a collection of sigma fields, sigma algebras, for each of those time indices, we call this whole collection of sigma fields a filtration if this collection of sigma fields gets finer with increasing time indices. So in other words, the sigma field which belongs to time I is a sub-sigma field of the finer sigma field j, fj, when j is larger than I. So we had already seen in certain examples in the past that the sigma field, or the degree to how fine a sigma field is, how large, how many sets are contained in a sigma field, this describes an effective resolution of our collection of all events into a grid, so to say, on which we can resolve certain events or not. And so whenever we have a sigma algebra which allows for more sets, which contains more sets, then this is a finer resolution of the space of the collection of all possible outcomes of an experiment, say, which is described by the total collection of omega. So a sigma, a filtration on a given probability space, is an increasing sequence of sigma algebras, which in a way you could think of a sequence of displays which allows us to display and to depict finer and finer pictures of the actual phenomenon, or of the actual random mechanism that is underlying our observations. So the finer, or the bigger the sigma algebra, the finer we can resolve the outcome of the random mechanism, which is initially described by this triple omega fp. And as an example, which is in many cases or in many regards already a complete description of what you should have in mind, let us consider the probability space which encodes the possible results of a 3 times coin experiment. So you have 0, 1 in the Cartesian power 3 as collection of all possible outcomes of this experiment, and you have the sequence of random variables as before, which projects onto the corresponding coordinate. And then for each time index k from 0 to 3, say, you can think of the sigma algebra, which is generated by the first k observations of this iterated coin toss. And so if I observe nothing, then my sigma algebra is just the trivial sigma algebra, which if I observe only the first outcome and all the other outcomes 2 and 3 are neglected in my observation, then I have 4 events only, namely those events which distinguish only in the result of the first coordinate and make no distinctions regarding all other entries of these triples. And finally, I have the second sigma algebra, which would then be generated by observing the first and the second outcome of this sequence of 3 coin tosses. That would be the collection of all events which make no distinction regarding the very last entry of the coordinates. And finally, the sigma algebra, which is associated to the index number 3, which corresponds to the full observation of all outcomes, of all 3 outcomes. That would be this sigma algebra F3. And this would be, in our case, the total power set, so the full power set. So I've indicated this in this drawing here. So the total probability space that we're dealing with in this example has the cardinality 8. So the trivial sigma algebra, which corresponds to no observations, is just the sigma algebra, as I said, containing of the empty set and the full set omega. The sigma algebra F1, which distinguishes triples only according to the first coordinate entry. This probability of this sigma algebra consists only of the empty set and the full set, and moreover it contains these 2 green bubbles. So I'm talking now about this graph here. So the sigma algebra F1, which I say again is the sigma algebra generated by the only first observation, by the random variable x1 alone, would be the sigma algebra which is generated by the green bubbles. And the sigma algebra F2, which corresponds to observing the first and the second result of my 3-fold coin toss, would be the sigma algebra generated by all those sets which do not distinguish regarding the third entry. And this is then the sigma algebra which is generated by the red bubbles. And you see it's a final resolution of my probability space. And finally the probability, the sigma algebra F3, is the full power set. So you see you have a sequence of finer and finer sigma algebras, or a sequence of richer and richer sigma algebras, which allow you to resolve all possible outcomes of the coin toss experiment in our case, even finer and finer. So here again, let me say it again. Here we had the example of a fixed probability space omega, where we could define a hierarchy, if you like, a hierarchy of sigma algebras, where as higher the index, the higher we have a resolution or given in terms of a sigma algebra, or the higher or the finer the sigma algebra is. And it's a hierarchy of sigma algebras in the sense that for a later moment of time, the sigma algebra that we deal with is finer, and in particular it contains all the previous sets which appeared in the previous sigma algebras, but then it adds new sets, a finer resolution. to the resolution that we had before. More generally, we can think of the concept of a filtered probability space or of a filtration not only when the index set is the integers or the real line. We could think of any index set which has a total order. In this case, we could also think of a filtration. And if we have a probability space with a filtration, we also sometimes talk of a filtered probability space. Okay. Now, we have now already the definition of a martingale, namely that omega fp be a filtered probability space. So we have an initial probability space together with a filtration. And the filtration here, as I had tried to explain in the previous example, represents our growing ability to distinguish events as time evolves. That's the right way to phrase it. As time evolves, which is, and time here is represented by this collection of time indices I from the set I. As time evolves, we are able to apply a more refined resolution to the collection of events. We have a more complicated and more elaborate understanding of the collection of events. And then we also, that's now the definition of a martingale, we have also a stochastic process whose time parameter space is exactly the same as this time parameters for the filtration. Then we call this stochastic process, which we assume to be real valued here, and martingale with respect to this filtration if, technical assumption, each of these xi are integrable. And I should say that integrability here for me means that either the positive, at least one of the positive or the negative part of this random variable has finite value, such that we can talk about the expected value of this random variable in a non-ambiguous way. So we assume integrability. Then we also assume that for each time index I, the random variable xi is measurable with respect to this sub-sigma algebra fi, or these fi's are supposed to be sub-sigma algebras of f. And we have the following important Martingale property, which represents what I said in the introduction of having constant expectation. We want that this process have constant conditional expectation. Namely, we want that if we compare the behavior of the process on two different time points, and the comparison is done by comparing the conditional expectation of one of the two with respect to the other, what we want is that the conditional expectation of the future behavior of this random process, given the information which is encoded in the sigma algebra at time I, if j is the future point, that this coincides, in fact, with the stochastic process that we are given now. So let me say it again. If we assume for a moment that we sit in time point I and we want to make a prediction on what the process might behave at a later time point, namely at time point j, which lies in the future, as seen from I, we can try to make a conditional expectation computation of this future behavior of the process given the information that we have now. And this given information that we have now is encoded by the by the sigma algebra fi. So the idea here is that if you think about this conditional expectation as being something which is associated to certain patches, so in a way it is to be understood as follows. So at the moment I, we have already observed certain things, which means that we know already that we are sitting on one of those patches which basically constitute the sigma algebra fi. And what I'm asking here is, okay, what's an xi, by the way, since it is measurable with respect to fi, xi has a constant value on that particular patch on which I'm sitting. And I want to compute the conditional expectation of xj, so of the behavior of the process at a later point, given the fact that currently I'm sitting on a patch, on this patch fi, on this patch which is belongs to the collection Fi. And what I want for the process is that this conditional expectation of the future, given the current state, that this equals the current state, the current value of my stochastic process. If that's the case for all possible pairs I and j, then I call the process a martingale. So in one line, a martingale is a process whose conditional expectations match exactly the latest observation. If instead of an equality sign, we have a greater or equal, which is to be understood that the value of a process on average in the future lies above the value that I'm having now, I'm talking of a sub-martingale relative to the filtration F. And if the inequality sign is the other way around, if what I have in the future on average in sense of conditional expectation is less than what I have now, then I call the whole process a super martingale. This is just convention. Let me give you an example, a casino example if you like. So suppose we have a repeated sequence of coin tosses independent with a success probability P, and let psi k be the corresponding random variables which assume values +1 or -1 depending on success or failure, or the other way around. And suppose we have a player, the whole thing takes place in a casino, and the player places a bet successively in each round, and he has a certain rule by which he places the magnitude of the bet. So he bets on success each time, of course, that's how we want to understand it, and he has a certain rule, says, okay, so in the kth round, I put a bet. So if you like, before I put I bet on the k plus first result, and the amount I want to put at risk is the maximum of the number of successes that I had before in the past, or to be more precise, I sum up the number of successes that I had in the entire past. So this is, if you like, the partial sum of successes or failures up to round number L, and I take the maximum number, say, that I observed in these partial sums when I vary this indicator between L between 1 and k minus 1. Sorry, I made a mistake here. So this is the amount that the player bets on the kth round. So before the kth coin is tossed, the player looks back in history, he evaluates all these partial sums that occurred in the previous rounds, and he computes the maximum number of this partial sums, and he doesn't want to place a negative bet, so that's why we take the maximum with a 0 here. It could happen theoretically that this number is negative, so he doesn't ever place a negative bet, and that's the amount that he puts at risk. So that's the amount, that's the actual euro that he bets. Okay, and so as a consequence, his win or loss after the kth coin has been tossed is this height, or the total amount of the bet, times success or failure. That's actually what he wins or loses following this strategy BK in round number K. And so the total amount of money he has lost or won when he does this up to round K is just the corresponding aggregate number of successes, or the aggregate number of wins or losses. So that's the total number, the total amount of euro that he wins or loses when he quits the game after round number K. And let Fk, so that's, but this xk is of course a stochastic process now. It's probably kind of complicated in the way it was produced. It's certainly not Markov because it depends on the whole past. So it's not a Markovian process. Markov chain theory here would not apply to the analysis of the process xk, but we can, that's the point here, we can at least identify this process as a martingale. Namely, we introduce the filtration as a sequence of sigma algebras, namely for index k, we take fk to be the sigma algebra which is generated by the first k random variables which describe success or failure of the respective coin toss. And then I claim that this sequence of total win or loss variables is an fk martingale, so a martingale with respect to this filtration, if and only if the success parameter of the coin is a half. If the success probability of the coin is bigger than a half, then we have a sub-martingale, and in the other case we have a super martingale for this process. Well, why is this true? Well, we have to check basically, okay, finiteness condition, this whole thing is, in each case, a finite total win or loss. So that's obviously an integrable random variable, this xk thing, so that's clear. And finally, we see by the definition of this eta k and the sum, we see, if you like, by a recursive argument, that the total amount that, or obviously the total amount that I won or lost after the kth round is obviously a function, which is a function of the first k realizations of the win or lose random variables. So therefore, in particular, it's an fk measurable function because it is representable as a function which depends on exactly those random variables which generate the sigma algebra. So therefore, the measurability requirement on this sigma algebra is also, on this sequence of random variables in this case is also satisfied. And I want to convince myself now of the Martingale property, which is number 3, which is about these these conditional expectations. So I'm trying to compute the conditional expectation of xk plus 1 given fk. So given fk means that since fk is generated by these finitely many random variables with finite possible outcomes, that this fk sigma algebra actually is really generated by a finite collection of disjoint subsets. So I'm really in this patch situation, the very intuitive patch situation for conditional expectation. And in order to compute this conditional expectation, I do a trick which I shall use many times in the future. Namely, I add and subtract 0 by adding and subtracting xk, so the stochastic process, the value of the stochastic process as observed one moment before. Now xk, as I just said, is fk measurable, so it just goes out as an additive term directly in front of the out of the conditional expectation. This is the identity operation here for this part. And then this difference of xk plus 1 minus xk is exactly this eta k guy, which is the difference in this partial sum. And the eta k has the representation that it's a psi k plus 1 times a maximum of these other random variables. But these other random variables, this factor, this max guy, represents the total amount that I'm betting in round number here, k plus 1, say. And this total amount that I place on the k plus first round was determined by looking at the success or failures of the previous k rounds. So in particular, this function here, or this term here, or this quantity, is again a function which is measurable with respect to this fk sigma algebra. So therefore, again, it goes out as a factor, as a multiplicative factor in front of the conditional expectation. And here I'm left with the conditional expectation alone of psi k plus 1, which is the success indicator of for the k plus first coin toss. And that is independent of fk. And so if we have an independent random variable, then this conditional expectation is just a full expectation. And then the number of this psi k plus 1, the expectation of this is 2p minus 1 plus xk. So then I see that this is xk, this is equal to xk, if and only if the first term, the first summand here vanishes, which is the case when p equals a half. Now, if p is greater than a half, then this number that I'm having here on the left-hand side is non-negative, and therefore I'm getting a sub-martingale. And if P is less than a half, then I'm having a number here which is less than, or no bigger than 0, so therefore I'm having something which is less or equal to xk, and that would produce a super martingale. So that's already the proof. By the way, I did the proof only for the case when I have a one-time transition, a one-step time transition, and by a simple inductive argument you can check that whenever you have this discrete or this finite collection of when the time parameter the time parameter set I, capital I, is a subset of the integers countable, then it's enough by an inductive argument to check the one-step martingale or sub-martingale property. Okay, many times we will talk about just a martingale without indicating what is the filtration that we want to work with. Sometimes the chosen filtration will be clear just from the context, and in other cases we just talk about a martingale when an explicit mention of a filtration was not done, and this then implicitly means that we are considering the filtration which is generated by the process itself. Namely, when, unless otherwise specified, typically we say process is a martingale, just a plain martingale, again, without mentioning a particular filtration, then this is, in most of the cases, to be understood as the process which is a martingale with respect to the filtration that the process itself generates. And as a consequence, whenever a process is a martingale with respect to a given filtration f, then it will also automatically be a martingale with respect to the filtration which is generated, which is a subfiltration by the adaptedness condition. This is just a side remark. Well, we can see and we can connect the theory of martingales that we're discussing now with what we did before in the context of Markov chains through harmonic functions as follows. It's just a nice little cross-correspondence here, which we sometimes also can use in the theory of Markov chains, and we shall do that at the end of this session another time. Namely, if we, for a moment, go back to our previous lectures and consider the case when we have a Markov chain, and the Markov chain property, let me say it again, and clearly the Markov property and Martingale property have nothing in common. There's no relation between the two. But sometimes you have processes which are both Markov processes and martingales. And these are very, very nice processes, in fact. But a priori, there is no connection between the theory of Markov chains and the theory of martingales. There's very little intersection, in fact, when it comes to the collection of processes which satisfy both conditions. Now, let us still then discuss the case that we are back in the Markov chain world. We're a Markov chain on a countable state space S, and let H be a bounded function on the states. Then we can, as we did already many times, consider the case when we evaluate the Markov chain by using H as an observable. That's now an integer valued correction. That's now a real valued stochastic process. And I claim that this real valued stochastic process is then a martingale for all possible starting laws lambda, if and only if H is harmonic with respect to the generator of the Markov chain. Okay, so a martingale, by definition, needs to be a real valued process. There's a possibility to extend it, if you like, for vector valued process, but let's not talk about this for a moment. So martingales are real valued processes. Markov chains are processes which assume values on general state spaces, which we can give names to the states. So only from that perspective, the two things have not so much in common. But we can convert a Markov process into a real valued process through applying an observable function H Okay, fine. So now we have a real valued process. And here the statement is that this real valued process that we derived or that we produced from the Markov chain, from the Markov process, is a martingale with respect to the filtration generated by the Markov process, the Markov chain, for all possible starting laws, if and only if this observable function is in fact harmonic. Harmonic with respect to this generator that we introduced in the context of Markov chains. Okay, why is this true? I give you only the proof of this if and only if statement in one direction. Namely, we want to convince ourselves that if the function h is harmonic, then in fact we have the Martingale property. Namely, for that we check zk plus 1, which is the application of h to the process xk plus 1, given the sigma algebra generated by the first k plus 1, say, observations. If you count. So then the Markov property, as we had said, tells us that this conditional expectation is just as good as if we start a new instance of the Markov chain at the latest time point of observation, and then we evaluate this one time step, which is the time lag between these two observation periods, if you like. If we evaluate the Markov chain, a new instance of the Markov chain in the starting point of the latest observation with the corresponding time step inserted into the observable h, that's our Markov property in the version of conditional expectation. And moreover, we know that this application here or this evaluation is nothing but applying the transition kernel of the transition matrix P to the function h once and evaluating it at the location which corresponds to the starting point, that's xk. But the harmonicity of the function h tells us that ph is nothing but h. So we have got h of xk, and we see that this is nothing but our zk. So here we started with the conditional expectation of zk plus 1 given this sigma field, and we end up with zk, which is exactly the Martingale property for zk. Okay, so we see this implication is correct, at least in the one direction. In the other direction, it's basically the same argument, and I leave that as an exercise. We collect a number of properties or consequences of the Martingale property or sub-Martingale property. For instance, one is linearity. So it's constants of a conditional expectation. That's conditional expectation is a linear operation. So therefore, the Martingale property is preserved when you take linear combinations of martingales. Yeah, you can think of two different stochastic processes which are defined on the same probability space, and then you can and those two processes are real valued. So for each realization of randomness, you can take the sum or the linear combination of the outcomes, which produces a new process. And if the initial two processes were martingales, then is the linear combination of the two processes. That's a straightforward consequence of the linearity of conditional expectation. Now, if we have two sub-martingales, and then if we pass to the stochastic process, which contains of the pointwise supremum, then that's also a sub-martingale. So this sign here, which I used, this V sign, I think I used it in the past already, is the max. Is a short way to write the max. So if I take two sub-martingales and I take the the pointwise max of the two, then this is again a sub-martingale. And the third property is if I have a sub-martingale and phi is a convex non-decreasing function, then the composition of phi with this sub-martingale is again a sub-martingale. Okay, as I said, the first property is a straightforward consequence of the linearity of conditional expectation. Let's prove the second one, namely that the pointwise maximum is again a sub-martingale if the two initial processes were. To see this, we write the trivial inequality that for instance, the M process, one of the two at time n plus 1 is less or equal than the supremum of mn plus 1 and nn plus 1. That's a trivial inequality. One thing is always less or equal than the maximum of this one thing with another thing. Okay, now I can take the conditional expectation of this inequality, but the conditional expectation on the left-hand side is an upper bound by the submartingale property of mk or mn. So mn or mk is less or equal to the conditional expectation of mk plus 1 given fk. That's the submartingale property of fk. But mk is less or equal pointwise than mk plus 1 and nk plus 1. And so therefore this inequality, this pointwise bound, is also correct for the conditional expectations, because conditional expectation is a monotone operation. The same argument is correct for the nk. So also the nk, by symmetry, is less or equal than the conditional expectation of the piecewise max of mk plus 1 and nk plus 1. So hence, since each of them is less or equal to that same quantity on the right-hand side, therefore the maximum of the two is also less or equal than the thing on the right-hand side. That's property 2. For property 3, which deals with the application of a convex function, okay, let us start here on the left-hand side with the conditional expectation of mk plus 1 after we apply phi. So the conditional expectation of phi applied to mk plus 1 given fk. Now Jensen's inequality tells me that this conditional expectation is greater or equal to if I do first the conditional expectation and then the convex function. So that's Jensen. Now the submartingale property of M tells me that this expectation of future behavior is more than the current state. So therefore this quantity which appears inside the phi function is bigger than this mk thing. And since phi is non-decreasing, or is increasing if you like, the whole thing decreases in value if I introduce or if I insert into phi the smaller number, which is then at the end the inequality that I wanted to make sure. As I had said in the introduction, I want to go through the most important properties and consequences here as quickly as I can. So I will now head towards what is called the dupe decomposition, which is in the end very intuitive and very helpful in order to make statements about martingales or submartingales. For this I need a further concept, which will be also very important later when we talk about financial mathematics. Namely, if we do have a filtered probability space and we have a stochastic process, then we call this stochastic process predictable if at time k the process is in fact measurable with respect to the filtration, with respect to the sigma algebra, which belongs to time point k minus 1. And if that's true for all possible time points k, then we call the stochastic process predictable. So what it says is that if the sigma algebra at time point k minus 1 completely describes all possible scenarios which I can observe up to moment k minus 1, if that's my interpretation, then it says that the value of the random variable which I look at time point k, that this value is already determined by the observations that are made at time point k minus 1, because it is by definition measurable with respect to the sigma algebra. And so therefore this sigma algebra at the previous time point, if that contains already everything that I could observe, then it is already, this random variable xk is already determined on this patch. So the patch is defined. There is no finer resolution of the random variable xk, and therefore if I know after time point k minus 1 the patch on which I'm sitting, then this determines the value of xk. And this explains the name predictable that we give for this. Okay, and with this concept we can now state a very useful and intuitive statement, which is called this Duke decomposition. Duke is an American mathematician after the Second World War. So namely that xn be a sub-martingale. So that's something that you just have to learn by heart, that sub-martingale means in tendency you have an increasing process, an increasing real valued process. And then the statement is that there exists a non-decreasing process, A, which is predictable, which starts in 0, and then there is a martingale such that this whole process xn, which in tendency is non-decreasing, in terms of conditional expectations is non-decreasing, can in fact be decomposed as something which is constant in time with respect to conditional expectation, so it's a martingale, and another additive component which captures the increasing part, so to say. So in other words, this sub-martingale can be decomposed into a martingale part and into an increasing process, which has really increasing trajectories. And this decomposition is unique under these conditions. I should probably remark or comment a little bit why this statement is on the one hand intuitive, but on the other hand not entirely trivial. Okay, after you have seen the proof, you will see, or you will think that it's actually a trivial statement, but nevertheless, before you see the proof, you should be a little surprised. So what is a sub-martingale in essence? So if it is a process that at each moment of time, whenever you do the conditional expectation, will still, so suppose this is the time axis, k, and you know, and these are the possible realizations, and you know that at time k you are in a certain location xk, and then you want to make a expectation, you want to take the average of all possible realizations of the process at a later time, j, say. And the sub-martingale property says that in a way, the trajectories which go up relative to the current state have higher probability than the trajectories which go below. And hence, the whole history or the whole path is not forbidden at all for the path or for the future behavior of the process to go down and from time to time, but the sub-martingale property says that the average behavior, when you take really the mean with all the possible realizations, the average behavior of this process should be positive. So in other words, you have a process which has an increasing average behavior of any type. It does not need to be, by the way, it does not need to be that of a linear function or whatever. So you have just some average behavior, and the process that is the sub-martingale will follow this average behavior it will follow this average behavior in the sense of the conditional expectations, but it does not necessarily mean that once in a while the trajectories do perform an excursion which is very much below this average line. So that should be your intuition of a sub-martingale. A sub-martingale is a process whose average behavior is positive, is increasing in time, but whose individual trajectories nevertheless can exhibit excursions which lay much below this average increasing behavior. And so what this theorem here tells us, that there is a decomposition of all these of all these green curves into parts which are of pure fluctuating type. So I'm not sure if I'm be able to depict this in a convincing fashion, but in a way it says that if you have a a realization, probably I should write it like this. If you have really a realization of your process, which now I depict in blue color, then this blue trajectory, that's what it says actually, can be decomposed into a still random trajectory, but which is really fully increasing, and it can be decomposed into another part of a trajectory, the green trajectory, which then will be really average, which will have an average zero behavior or an average constant behavior. So every blue trajectory, which is the actual process trajectory, can be decomposed into a really non-decreasing red trajectory, which is still random, but it's really non-decreasing, and into a green trajectory, which can be understood as a trajectory of a martingale, which is something which is constant over time. So you can subtract, if you like, the positive trend in a unique fashion, and this positive trend will be even predictable, in the sense that the positive trend is determined already before you actually evaluate the next degree of randomness. Okay, how do we prove this dupe theorem? As I said, the proof is easy in a way once you understand the actual statement. Namely, we introduce as this increasing process the process of partial sums of conditional increments. So the conditional increment of the process is defined to be the difference of the expected value of the process in the time step from k minus 1 to k, and the actual value of the process at time k minus 1. So the difference between the conditional expectation of the process at the very next moment towards the actual state of the process at the current moment, this difference is what we call the conditional increment. And by the submartingale property, this conditional increment, before we prove the dupe theorem, I should probably also mention that this, for instance, this submartingales, they play an essential role as a modeling device, or as the standard models for the behavior of stocks on the stock market, right? So, of course, you cannot expect from a stock to go upwards all the time, but what you would most likely want to have is a stock which at least has a positive trend or so. And the submartingale is basically the stochastic model that features this. So a submartingale is a prototype model for a stochastic stock price dynamics. Fine, so let's prove now the dupe theorem, or the dupe decomposition theorem, because actually there are several theorems which are named after dupe. Namely, we introduce the process A, which will be the increasing process, the increasing part, as the process of partial sums of what is called the conditional increment of the process X. So A, the process A, is the, as I just said, the partial sum process of the variables Sk, where Sk is the conditional increment of the X process at time k. So it's the increase that the process X is doing from time step k minus 1 to time step k, where at time step k we do not actually evaluate the process, but we rather replace the process by its conditional expectation given the filtration fk minus 1. So in that respect, it is rather the expected increment that the process will do once we are at time point k minus 1. So sk is the expected increment, expected conditional increment, conditional on the information which we have available at time point k minus 1. And by the submartingale property, this sk is a non-negative random variable. Hence, if we sum up all these sk variables we will obtain an increasing process because we sum up non-negative random variables. And we define this partial sum to be 0 at time point 0. Okay, AK is therefore an increasing process, and by construction it's predictable, because what you need to evaluate at time point k for the next evaluation of the AK process is exactly this conditional expectation as an additional summand in this partial sum, but by construction this additional summand is fk minus 1 measurable. So therefore it is in fact a predictable process. And then if that is our candidate for the AK process, then we have basically no other choice than to set mk or mn to be xk minus ak. And what is left to show is that this mk process is a martingale. So we compute the conditional expectation of mk given fk minus 1. Then by definition of the process ak, this is the partial sum, this is the difference between ak, which is appearing here inside the conditional expectation, and ak minus 1, by definition of ak, is exactly this conditional increment. And if we insert this into the definition, or if we insert this and use it in the definition of mk, we get that the conditional expectation of mk is the conditional expectation of xk minus ak, where we write ak as ak minus 1 plus sk. So therefore this partial this conditional increment is appearing, and the ak component can be taken out of the conditional expectation because it is fk minus 2 measurable, which is a sub-sigma algebra of fk minus 1. Okay. And then by construction, we see that in the conditional expectation of xk minus sk, there is the conditional expectation of xk effectively appearing twice with a different sign, and the only thing that remains is the conditional expectation of xk minus 1, which is of course fk minus 1 measurable. So this is the result of this. So the result of the conditional expectation is just xk minus 1. And if we plug the things together again, we see that we are left with mk minus 1 again. So in fact, we see that M is a martingale, and the claim, as long as the existence of such a decomposition is concerned, is proved. It remains to show the uniqueness. So for that reason, assume you have two decompositions of the type that was discussed. Then we can. Then it follows necessarily from this representation and the fact that ak is already measurable with respect to fk minus 1, that ak minus 1 must necessarily be this conditional increment of the x process. And the same argument, of course, applies to ak prime, that ak prime must be the conditional increment of the xk process. So therefore, these two increments, ak minus 1 and ak prime minus 1, must be the same for all k greater or equal to 1, and they are both assumed to start in 0. So therefore, by induction, you find that the ak's processes are the same, and since they are compensators, since they both compensate for the xk process, then the mk must be the same. So that also proves the uniqueness of this decomposition. Okay, we want now to extend this Martingale property or Martingale equality to the case when the deterministic times are replaced by, again, stopping times. So we will encounter the concept of a stopping time again, but now in the slightly generalized concept when we define the stopping time relative to a given sigma algebra or sigma filtration of the probability space. So let omega f P be a probability space which is equipped with a filtration. Then we can talk of a random variable of omega which assumes values in the extended integers, and we call such a random variable which assumes values in the integers Here, of course, integer value or value 0 is also admitted. So we call this a stopping time with respect to the filtration f if the event that the stopping or that this random variable tau assumes values no more than k is contained in the sigma algebra with time parameter k. Now, if you think of a stopping time, as we had discussed already in the context of Markov chains, as a first hitting time, for instance, what we were requiring there is that this event is representable through looking at the stochastic process up to moment k alone. Now, if this sigma algebra fk here is in fact generated by a stochastic process, then this condition is absolutely the same, but in general we may think of sigma algebras which are not necessarily generated by the stochastic process. And then what we want to make sure is that the event which is described through this condition that the stopping time be no bigger than k, that this is an event which can be completely resolved and completely depicted with the collection of events which is given by the sigma algebra fk. So again, let me say that the sigma algebra fk is the collection of all events that we can reasonably observe and describe by some exterior information or some observation which ultimately is encoded in the sigma algebra fk. And when, for instance, this sigma algebra is generated by the trajectories of a random process, then this is exactly the collection of events that we can detect by looking at the stochastic process up to moment k. But in general, we might generalize this idea and say, okay, we have a certain increasing ability to detect and describe events as time progresses, and at each time we have this collection of events which hypothetically can be described. And what we want from this integer valued random variable is that the event that this random variable tau assumes values no bigger than k is among those events which can be described only by looking at the events up to time k. That's what is said. So also here, this is a way to say that this time tau, or this, which is to be interpreted as a random time, that this random variable tau cannot look into the future. And again, we have this example of this first hitting time of a, say, Markov chain. Then this first hitting time of a Markov chain is exactly a stopping time relative to the filtration which is generated by the process. Okay, and we will now, once we have understood this concept or introduced the concept of a stopping time relative to filtration, we will now be able to extend the elementary Martingale property that we had introduced at the beginning of this session to more complicated non-deterministic times. But before that, we shall introduce a little more notation, namely, if we have two stopping times, sigma and tau, then the pointwise supremum, the infimum, and even the sum of the two stopping times will again be stopping times. The proof of this is not complicated. So, for instance, if we want to convince ourselves that the pointwise maximum of two stopping times is again a stopping time, then for the maximum of two stopping times to be below the number k or no bigger than the number k, that is in fact the intersection of the two conditions that both stopping times simultaneously are no bigger than k. Here's a little misprint. And since each of those events by the condition on the stopping time sigma alone and tau both are in the sigma algebra fk, so this is an fk and this is an fk by condition of sigma and tau being a stopping time, so then the intersection of the two events is also in Fk. And likewise for the other two constructions. So okay, we can recombine collection of stopping times to give new stopping times. And if, for instance, you think of a stopping time being some sort of an alarm clock, which triggers also, some sort of an alarm bell that is triggered by certain events, then, for instance, the maximum of the two stopping times, where each of those stopping times is related to a certain alarm mechanism, would be the alarm mechanism that is invoked and only at the moment when both alarm mechanisms alone give a ring. So once both have rung, then the actual maximum of the two stopping times will give an alarm, and likewise the infimum. And from this perspective, it is clear that these constructions also give you a yield stopping times. Okay, and once we have a stopping time, we can also define the sigma algebra, which is generated or which is associated to such a stopping time relative to a filtration F. And that's now a slightly technical definition, but it is useful. So we say that this sigma field, which is associated to a stopping time, consists of all those events from the initial sigma field, such that when you take the intersection of this event with any sublevel set, as we say, of a stopping time, that this is in fact an element in the sigma field with index k. So in a way you could say that an event E is in the sigma field generated or associated to the stopping time tau if it is foliated into the different levels of the stopping time tau, where each of these foliating subsets is in fact nicely describable by the information that is available at the respective level of this respective time when this stopping time tau or this alarm has rung already. So if that's the case, if an event E is foliated nicely into sublevel sets according to the stopping time, according to the values of the stopping time, such that the corresponding subsets are in fact reasonably describable through the information available at the respective time, then we say that this event E is an element of the sigma algebra associated to this random time tau. We have then the following properties of this sigma algebra associated to a stopping time, which I shall not prove to you in detail, but it's a kind of straightforward exercise playing with the definition. Then first, F tau is in fact a sigma algebra, which is a sub-sigma algebra of F. Second, if you have two stopping times where the one is bigger than the other, then the corresponding inclusion is true for the induced sigma algebras. And third, the stopping time which is obtained by taking the minimum of two stopping times is the same as the intersection of the respective sigma algebras for the two stopping times which were used for that construction. So this is an exercise which I leave to you. Then one kind of nice property which I would like to show to you is that the operation or the construction of stopping a process at the stopping time, or effectively evaluating a process at the stopping time, is a reasonable process, and it yields a measurable random variable in the following sense. So suppose you have a stochastic process which is adapted to the filtration F dot, which is to say that for all, so the adaptedness here, I'm not sure if I had introduced that properly. So we say that X is F dot adapted if for all K, the random variable xk is Fk measurable. That's what we call an adapted process which is adapted to a filtration. So if we have an adapted process to a filtration F, and if tau is a stopping time relative to that filtration, and if the stopping time assumes only values in the integers, or in the integers including 0 but not infinity, then we can consider the following map that maps every omega from omega space into the state space of the process. Here it's not assumed that the state space is the real line. It can generalize to general state spaces. Namely, x tau is defined as the evaluation of the process at the moment which is dictated or which is predicted or prescribed by the stopping time tau. So x tau now is a combined variable, which is a random variable which needs the full stochastic process, and it needs the stopping time tau. And what it does is it evaluates the process at the stopping time. This is the map x tau. This is one random variable, and the claim of this proposition is that this is in fact an f tau measurable random variable. So this random variable is measurable with respect to the stopping time that is associated to this, measurable with respect to the sigma field which is associated to the stopping time. Okay, to prove this, let us first take a measurable subset of the target space of this stochastic process, and let's compute the inverse, the pre-image of this set as a subset of omega, and this pre-image can be foliated according to the different levels that the stopping time can assume. This is done here. It's just a disjoint decomposition. And we note that this decomposition is a decomposition into subsets which are measurable with respect to the respective sigma algebra fk, where k is the ranges over the values of the stopping time. And why is that so? Because if we look at this intersection of two events here, this intersection here is of course by the condition that tau assumes value here, the level k is the same as if we replace in the pre-image of x tau the value tau, or the stopping time tau, with the number k, and there we see that this is actually a subset of the pre-image of the set A under the stochastic process at time k, intersected with this subset tau to the minus 1 of k, which is fk measurable. Hence, if we now take the pre-image of this set with the sublevel set L corresponding to the level L of the stopping time, then this intersection, and here, by the way, I made a mistake. This intersection here is the wrong sign. It's the union, right? Because we take a disjoint union of all these possible events, so that needs to be corrected. This is the union. Also here, it's the union. And likewise here we have the union. So, in all these, so when we take the intersection with the sublevel set associated to the value L for the stopping time, the same decomposition is correct, but the union needs to be taken only with up to the time index L. Each of these individual sets belong to the sigma algebra fk, where k here is the running index, which runs from 0 to L, but these sigma fields are all increasing, so all this is contained in the maximum sigma algebra, which corresponds to the level L, so that's in then the sigma algebra fl, because it's a union of subsets of the sigma field fl. Okay, so therefore, in fact, this evaluation of a stochastic process at a stopping time is a new random variable which has a reasonable measurability property. And now finally we can formulate the optional sampling theorem, which I had announced at the beginning of this lecture, which reads as follows. Let X be a submartingale with respect to a given filtration F, and suppose you have two stopping times, sigma and tau, where tau is greater or equal to sigma, and assume that there is some number n naught which is a uniform bound to these two stopping times, a uniform upper bound. Then we can take the conditional expectation of the evaluation of this stopping time we can take the conditional expectation of the stochastic process at random time tau, at the stopping time tau, condition it on the sigma field associated to the second smaller stopping time sigma, and what we obtain is a random variable which is greater or equal than the stopping time, than the stochastic process evaluated at the smaller stopping time, almost surely. So you see that this is precisely the submartingale inequality, which we state here another time. But here we have the submartingale inequality now for random times. This is this generalization that I had announced. So we can also obtain this submartingale inequality, and in case of a martingale, correspondingly we get the martingale equality, not only for deterministic times S and T, but also for random times, provided they are both stopping times, and provided here that there is an upper bound, an absolute value, an absolute number as an upper bound for both of the stopping times. We will prove this in 3 steps. First, we assume that X is not a submartingale but a martingale. Later, we will use the Disjoint Decomposition to conclude from a submartingale, to conclude that from the martingale case to the submartingale case. So, and the second assumption we want to make, which is stronger than the assumption of the claim, is that the bigger stopping time tau is in fact deterministic. And what we want to show is that we have this conditional expectation equality in this case. So what we want to prove is that the conditional expectation of xt given f sigma is equal to x sigma. That's what we need to prove. Okay, so for that reason, we choose any set which belongs to the sigma field f sigma. So to the sigma field which is associated to the stopping time sigma. And what we want to show ultimately, and will show now, is that this expectation of x tau, which in our case is t, times this indicator function of the set A, is the same as if we integrate x sigma with respect to the with the indicator function of the same set A. This is nothing but to say that the local average, if you like, of the xt random variable computed on a subset of the sigma field f sigma is the same as the local average of the random variable x sigma when integrated over the same subset A. This is our local averaging condition, which was critical for the identification of the conditional expectation. It was exactly this. The other condition that we need to make sure regarding the measurability of this would-be conditional expectation is satisfied because we had just checked that x sigma is in fact f sigma measurable. Okay, so we want to evaluate this integral here in case when tau is a t, and as before we decompose this integral into integrals over subsets which correspond to the levels that the second stopping time sigma can attain. Now sigma is no bigger than t, so therefore only the values from 0 to t for the stopping time sigma can occur. And if we take the intersection with the level set sigma equal k on each of those integrals, then we see by the property that the set A was taken from the sigma algebra associated to the stopping time sigma, we see that this is in fact the indicator function of a subset of an event which belongs to the sigma field Fk. This is true because A was not an arbitrary A, but A was an event from the sigma field associated to sigma. And that is just to say that those intersections which we have here exactly belong to the sigma algebra for deterministic time k. Now we know that x, that's the assumption of this step, is a martingale, so therefore the local average of this martingale at time t, when computed on a subset which belongs to the sigma field Fk, is just as good as if you take the local average of the random variable which has of the stochastic process at time k, where k is exactly the time to which this element of the sigma field belongs. So therefore, in this integral, due to the Martingale property, I can replace the xt variable by the xk variable. That's exactly the Martingale property here. And now I can, since I'm working on this intersection, I can equally write this k here on this subset as an x sigma. And now I see that I have decomposed an x sigma integral with respect to the different values that the x sigma can assume. So I can reassemble this decomposition and arrive at the claimed equality. So this shows that in fact the conditional expectation of xt given the sigma field f sigma is x sigma in case when x is a martingale. Now, second step, assume x is a martingale and the stopping time tau is in fact a real stopping time, but has an upper bound by an absolute number. So here's a misprint, here's a tau. Now assume we are in this situation, so martingale, but two stopping times. Then we have this upper number n0, which is an upper bound for both stopping times which appear, and hence we can write first by using what we had done in the first step, x sigma as x evaluated at this absolute time point n0 conditional to f sigma. But then we know that this sigma field f sigma is a sub-sigma field of f tau. And so by the projection property, we can first project this x and n naught random variable to a finer sigma algebra before we do the projection onto this very coarse sigma algebra f sigma. Because sigma is smaller than tau, then f tau is finer than f sigma. But using again our previous step number 1, we know that this conditional expectation is exactly x tau. And hence we have exactly the equality which we were looking for, namely that the x sigma random variable can be written as the conditional expectation of x tau given f sigma. That is the case. It's almost finished now because we have shown that this martingale or submartingale inequality is true and for these random times in case when the submartingale is in fact a martingale, And now we make the last step actually to the sub-martingale. But by dupe decomposition, we know that every sub-martingale can be written as a sum of a martingale and a non-decreasing predictable process. Okay, so we write out the conditional expectation of x tau given f sigma and insert dupe decomposition, which says that x tau can be written as a martingale plus an increasing process conditioned on f sigma. Now, this A component is a non-decreasing process, and tau is bigger than sigma. So hence, if I evaluate the A part of these two processes, not only at tau, but already at sigma, I get something which is smaller, just because A is non-decreasing. So evaluating it earlier, this A part gives something which is smaller in value. So here I'm just using a pointwise estimate, which for the two random variables A tau and A sigma. Now A sigma is obviously measurable with respect to F sigma, so therefore I can just take it out of the conditional expectation without any change. And I'm left with the conditional expectation of M tau given F sigma. This is then, by what we had found before, is the same correction, and here's again a misprint. This is in fact equal to M sigma plus A sigma, which by dupe decomposition again is X sigma. So this concludes our proof of the optional sampling theorem, which is already a first real result in the theory of martingales or submartingales. And we will have in the exercise sheet an example which is sometimes called the St. Petersburg paradox about doubling the bet when playing roulette or something like this, which shows that the martingale identity is not true in case for stopping times when you have not ensured that the stopping times which are involved are bounded. So the boundedness assumption on the stopping time can in general not be omitted. That's an important point here. And again, we will have an exercise we will have a problem in the exercise sheet which will demonstrate that things can go wrong if you don't make sure that this assumption is satisfied. Okay, this concludes our first rush and first encounter with martingale theory. We will continue this for at least 2 more sessions, I think. But I wanted to give you a first, if you like, application of what we have learned today by considering again this Dirichlet or hitting time problem that we had discussed in different ways already several times in this part on Markov chains. Namely, let xk be a Markov chain with a transition matrix P on a state space S, which is countable as usual. And suppose we have 2 sets, A and B, as before, and we want to compute the probability that we hit the set A before we hit the set B. And we want to assume that either of the two happens with infinite time with probability 1, or even more so, we want that this is absolutely bounded, which let's assume for a moment that this is guaranteed by the specific setup of this Markov chain. Okay, then I claim that this function, which is a function of the starting position, so I start here as we had many times before, I start here and I do my Markov chain and I want to know what's the probability that I hit A before I hit B, and my starting point is I. So as a function of I claim that as a function of I, this solves the following linear algebra style equation, namely on the subset of points in A. This function is 1, obviously, it's 0 on the complement, on B, and else it is harmonic elsewhere. And I claim that this is the solution to this function here. H of I solves this problem, and I want to show this by using, anyway, my optional sampling theorem. Namely, assume for a moment that I have a solution to this linear algebra equation. Assume for a moment I have a solution to this linear algebra equation. Then, as long as the process travels through the complement of A and B, which is before I hit the stopping time, then this process is a martingale. This is a simple consequence of the fact that the function h is harmonic. It's basically the same argument that we did before when we talked about Markov chains in the context of martingales at the beginning of this session, and the harmonicity of such an observable enforces that the corresponding composed process produces a martingale. Here we have a harmonic property of the function h is harmonic only outside the sets A and B, or outside the union of the sets A and B, and therefore this Martingale property is correct as long as we evaluate the process only before the stopping time is attained. That's why this is a martingale under any measure, in fact, but in particular under the starting measure, which is the Dirac measure in point I. And since it's a martingale, it has constant conditional expectations, and in particular, it has constant expectations. So therefore, the expectation of this Z process at time 0 is the same as the expectation at any other time, but at Z equals 0 under the starting measure I, the process is h of x0, which is h of I. But on the other hand, if we insert as the evaluation time the stopping time of tau A and B, then this, since it's a constant expectation, it's the same in expectation. So the expectation of this process at the stopping time, tau A union B, is the same as the expectation of Z at 0, and this is then by definition of our solution V. And I should probably have made a mistake. I made a little mistake here. I apologize. So I should have written a V here, right? So I assume I have this solution and I compose my process with the solution V. Okay, so anyway, so at position V, position I, at time point 0, Z of 0 is V of x naught. X naught is I, so I get Vi. And at the hitting time of the sets, at tau A, union B, when I evaluate the process there, I have only two possibilities, namely at the stopping time I am sitting in set A or I'm sitting in set B, but by the definition of V, which in this case is an indicator for the two cases, the V function gives a 1 only to the event that the two stopping times, among the two stopping times, the stopping time for the set A was the smaller one. So this evaluation of V on the X position evaluated at the stopping time is nothing but an indicator for the event that, in fact, tau A was the first heating time of the two. And this is then, by definition, just this number. So we see that if we have a solution to this Dirichlet problem, then this solution of this Dirichlet problem can be represented like this. And this was proved by using effectively the optional the optional sampling theorem that we had just proved for Martingales.